Welcome to the second video in this series, where we learn how to read and understand graphs, a skill that makes it a lot easier to link graphical representations to their real-world meanings. In our previous video, we had Sam walking at 3 different velocities over time, while also standing still for some periods of time. We saw how his displacement or distance from a starting point could be represented on a graph of displacement over time, and how that graph could be converted into a graph of velocity over time by considering the change in position over the change in time. We also saw that multiplying the velocity by time brought us back to the displacement again. If you still need to watch the first video, there's a link in the top right that you can follow. Today we are adding acceleration to the picture, so let's get going. Hello and welcome to the main course. Dish up some food for thought. While the first video was set up in order to be a simple introduction to displacement and velocity, I hope it bothered you a little bit that Sam's velocity changed instantly every time that it changed. When starting off or stopping, there was no gradual increase or decrease in velocity. For example, when setting off from his car, his velocity of 0 meters per second changed to -2 meters per second right away. Our line segments indicated only constant velocity, namely 0, 1, 2 and -2.5 meters per second, with a sudden jump at each change. This translated into only straight line segments on the displacement graph. This is not how things work in real life. Even Usain Bolt takes a couple of seconds to get up to speed. So today we are adding acceleration to our scene. Displacement is a distance given in meter in our example. Velocity is the rate at which this distance changes, so it's given in meter per second. Acceleration is the rate at which the velocity changes, so it's given in meter per second, or meter per second squared. To keep things simple, this time Sam is going to take one uninterrupted walk to his car and another back to his picnic table at the same speed. However, both these walks will start with a gradual increase in speed and end with a gradual decrease in speed. Let's see how that influences the graphs. Sam will soon set off with an acceleration of 0.4 meters per second squared. This acceleration will last for 5 seconds until he reaches 2 meters per second, which equals the acceleration multiplied by the time it was in effect for, or 0.4 meters per second squared times 5 seconds. He then keeps going at 2 meters per second for 20 seconds. Since his acceleration is now 0, we are in the familiar case where velocity stays constant and displacement is a straight line segment. But for the first 5 seconds, velocity started off at 0 and increased slowly. This means the displacement started off changing only slightly and then more and more as velocity increased. This gives us a curve on the displacement graph rather than a straight line. When he gets close to his car, the same thing happens, but now his velocity decreases gradually from 2 to 0 meters per second over 5 seconds, due to an acceleration of -0.4 meters per second squared, or a deceleration. When he starts heading back, acceleration is still negative, since his velocity decreases further from 0. Remember that velocity has a direction, and heading back is a negative velocity. So the acceleration, velocity and displacement graphs now form mirror images of the journey to the car, since everything happens at the same absolute rate, only in the opposite direction. Let's have another walkthrough and concentrate on what happens when we calculate the areas under the graphs and the slopes of the graphs. We actually need derivatives to calculate the slope of the curved displacement graph, but take my word for it for now that it changes linearly from 0 meters per second to 2 meters per second over the first 5 seconds. This is what is represented in the velocity graph for the first 5 seconds, as a straight line increasing from 0 to 2. If we calculate the area under this straight line, using the formula for the area of a triangle, we get a half times 5 times 2 equals 5 meters, which is the distance that Sam has moved from his starting point. On the other hand, if we calculate the slope of the velocity graph, we get 2 minus 0 meters per second divided by 5 minus 0 seconds, or 0.4 meters per second squared, which is what the acceleration graph indicates for the first 5 seconds. Next, the slope of the displacement graph remains at 2 meters per second for 20 seconds, which is again confirmed by the velocity graph at y equals 20 and the zero acceleration. You can calculate the area under the velocity graph to get the 40 meters displacement. And the slope gives you the 0 meters per second squared acceleration. Nearing the car, Sam reduces speed for 5 seconds. The slope of the displacement graph now changes from 2 to 0 meters per second, and this is again represented in the velocity graph, where the straight line heads back to 0, as well as in the acceleration graph, where acceleration is now minus 0.4 meters per second squared. After donning his backpack, he starts walking in the opposite direction. The calculations are fundamentally the same as in the journey to the car, but this time in the opposite direction. Note how the acceleration is negative at the start of the journey, since Sam is increasing his speed, but velocity is still in the negative direction. When he gets close to the table, his acceleration is positive, since this has to curb the negative velocity and drag it back to 0. So the rate of change in his velocity is positive. Let's quickly consider another very practical example, that of gravity. Now, real gravity on Earth is closer to minus 9.8 meters per second squared, but we'll work with minus 10 to keep the calculations simple and rounded. Imagine a rock being flung straight up into the air at a certain velocity and being dragged down again by gravity. How would its displacement, velocity, and acceleration change over time? In our example, our rock starts its upward journey at 40 meters per second. The acceleration on the graph on the right is provided by gravity and is therefore a constant minus 10 meters per second squared, since we've defined the upward direction as positive. This means that for every second that passes, the velocity of the rock decreases by 10 meters per second. So, after 4 seconds, the rock's velocity has decreased by 40 meters per second, which means it has reached its highest point in the sky, after which it starts falling down faster and faster. Its velocity keeps decreasing, or its downward speed keeps increasing. After another 4 seconds, it hits the ground and comes to a standstill. Since the displacement did not happen at a constant velocity, the displacement graph is a curve rather than a straight line, and like the rock, the rate at which this curve rises on the y-axis keeps decreasing until it reaches its turning point and starts falling down again. Let's have another walkthrough and concentrate on what happens when we calculate the areas under the graphs and the slopes of the graphs. If we use derivatives, we can show that the slope of the displacement graph changes linearly from 40 meters per second to minus 40 meters per second over the 8 seconds. This is exactly what the velocity graph shows. Calculating the slope of the velocity graph, we see that the change in y is 40 minus 40 meters per second divided by 8 minus 0 seconds, or minus 10 meters per second squared, which is exactly what the acceleration graph represents. So, when we divide meters by seconds, we get meters per second, and when we divide meters per second by second again, we get meters per second squared. This is equivalent to the real-world idea of dividing displacement by seconds to get velocity and dividing velocity by seconds to get acceleration. On the other hand, as we calculate the area under the curve using some variant of x multiplied by y, we move in the opposite direction between graphs. So, the minus 10 meters per second squared of acceleration multiplied by 8 seconds to get the area of the rectangle leads to a change of minus 80 meters per second in velocity, taking the rock from the initial 40 meters per second to the minus 40 meters per second when it hits the ground. And the areas of the two triangles formed by the velocity graph are 80 meters and minus 80 meters, which equals the rock's displacement into the air followed by its fall back down to earth. Finally, we have a quick look at the formulas for the three graphs. The acceleration is quite easy, y equals minus 10, a constant. For the velocity, we have a straight line formula, y equals minus 10x plus 40, with a slope of minus 10 and an intercept of 40. For the displacement, we have the formula of a parabola with zero intercept, namely y equals minus 5x squared plus 40x. In future videos, we will look at how these functions are integrals and derivatives of each other, and what the constant that you can add to integrals mean practically. But this is enough for today.